Greetings everyone. Myself Janish Panchal and I'm a second year master student here at CEPT University. In this video, I'll be sharing my portfolio work for a high-rise commercial project, mainly focusing on the plumbing modeling, clash detection, and data-driven coordination. Talking a little bit about our project, the urban rise was situated here in Ahmedabad city. The project timeline, type of contract, and the project cost, along with the other details, are mentioned on the screen itself. For our studio scope of work, we had taken basement 1 and second floor. Talking a little bit about the plumbing modeling, so myself Janish Panchal was the plumbing consultant as the studio role for this particular project. And in that we developed the LOD 300 models for plumbing, and the modeling challenges which we faced were the maintaining pipe slopes, correct fixture hosting, updating sizes after the revision, and routing the congested zone as well. The activity was to generate the LOD 300 models for basement 1 and second floor itself, and the duration and the start date and end dates are mentioned here for. Here we are focusing on the design side challenge in our project. In our project, we saw that every discipline was working in isolation, so communication was fragmented and there was no proper common data environment. Our response to that was to bring all the LOD 300 disciplines and run a structured class detection while using Autodesk Construction Cloud as a single platform for models, drawings, and issues. And along with that, we also used Navisworks majorly for our class detection part. All the decisions, minutes of meetings, and all of the RFIs were generated as well to linking it back to the common data environment. So everyone is working on the same current information rather than exchanging scattered files and messages. This slide is about the first class test between the architectural and structural model at LOD 300. We exported both the models, appended them in Navisworks, and ran a hard clash test with a 10 mm tolerance. In the first one, we got about 117 clashes, mostly modeling issues like misaligned walls, missing openings, beam cutting through walls or slabs. These were assigned back to the respective model authors, corrected in Revit, and the test was rerun. After a few cycles, we achieved a clash-free architectural and structural model, which then became the reference for the services coordination. Once the main frame was clean, we moved to inter-services coordination. Here we check fire protection versus electrical, fire versus plumbing, plumbing versus mechanical, and mechanical versus electrical using the same 10 mm tolerance. Some pairs like fire versus plumbing and plumbing versus mechanical directly came out with zero clashes, while others, such as mechanical versus electrical, had isolated clashes. These were all resolved with small root and clearance adjustments between ducts, trays, and pipes. And then the rerun confirmed that the services zone were clash-free before freezing the layout as well. After clearing the individual service clashes, we carried out a final verification set where the resolved architectural and structural model was checked against the resolved service model. The aim was not to hunt for hundreds of clashes, but to confirm that there are no residual constructability issues at LOD 300. The Navisworks test used the same 10 mm rules, and the checks were done for mechanical, electrical, plumbing, and fire protection step by step. This step gives us a confidence that the integrated model can be used as the coordinated design package and forms for the base for later LOD 400 detailing and 4-dimensional and 5-dimensional work as well. Talking about the cost language which we have seen. So in this particular slide, we have converted what could be a possible cost rerun for our particular project as well. So we can see that we have taken one typical clash and converted it into a cost language. If the same clash is found on site rather than in the model, it leads to core cutting, chipping, additional concrete, extra labor supervision time, and sometimes delay in pour sequence as well. In the report, we estimated these rework items and compared them with the design side effort, which is basically extra BIM coordination time, one more clash run, and a coordination meeting. The message here is that spending a little effort in the early model based coordination avoids significantly higher rework cost and disruption at site, which is why design coordination and data integration tests are a key investment rather than an optical exercise. Moving forward with the Power BI integration. So the reason why we developed or generated a Power BI template or a Power BI component was that Power BI connects directly to the common data environment and it converts model and site updates into interactive dashboards. Progress, clashes, and key quantities are visualized on a single screen, helping consultants, site engineers, and management teams to review the status quickly, as well as automated refresh keeps the dashboard up to date so project decisions are based on current information rather than specific static reports. This portfolio demonstrates a complete digital workflow from modeling and clash resolution to analytics-driven monitoring. Coordinated plumbing and MEP models reduce on-site conflicts while structured data flow into Power BI to support transparent reviews. Together, these steps improve constructability, reduce rework costs, and create a more collaborative environment for all project stakeholders. Thank you.